Last example, draw a network diagram for a project given in table. Hurry and try to storm your brainstorming. The table shows that, of course, activity A has no predecessor, B belongs to A, C belongs to B, D has A, E has D, F has C and E, G has D, H has D, I for H, J for H, K for F and H, L for G and J. Okay, now let's follow how the diagram expresses the givens in the table. We need to, I would like you to state that if we need a dummy activity or not in this table. Okay, just again, this table emphasizes that two or more than one activity can start from one event. Two or more than one activity can end at one event. Now, this is quite enough introduction. Actually, it is an introduction to understand the nature of building a network diagram. This is not, of course, the full details, because these two methods are very rich and it requires more than 3 or 4 lectures to cover the requirements of this. Okay, well, this is quite enough for the purpose of our course and discipline. Thank you very much. Referring to the previous slides, let us add the last step 5, finding the optimal solution. The value of Z at various points of the region of visible solution are calculated. The optimum, maximum or minimum Z among these values is noted. Corresponding solution is the optimal solution. Let's see. Solve the following LPP, linear programming problem. LPP stands for linear programming problem, graphically. What is given here? X maximum or max Z equal 3x1 plus 5x2. That's mean. Firstly, this linear programming problem about what? About profit maximization. Once it indicates max Z. There are two decision variables, x1 and x2. 3 is the profit of 1 unit of x1, while 5 is the profit of 1 unit of x2. Now, subject to the following constraints: x1 plus 2x2 less or equal 2000, x1 plus x2 less or equal 1500, x2 less or equal 600. These three constraints means that these two products, x1 and x2, pass three phases of production or three machines or whatever, three processes respectively. And actually x1 is a non-negativity condition, x1 and x2 more or equal 0, obviously. So let's step by step view how we can apply graphical method solution. First, to represent the constraint graphically in inequalities are written as equalities. Every equation is represented by a straight line. 2. To draw the lines, 2 points on each of the lines are found as indicated in the following table. Intercept. Now, step 1. Convert the constraints into what? Into equations. First step, to convert the constraint into equation. What that means? That means constraint 1 will equal x1 plus 2x2 equal 2000, and x1 plus x2 equal 1100, and x2 equal 600. Three constraints. So using geometrical methods to find the value of x1 when x2 equals 0, and to find x2 when x1 equal 0. Let's see how we can do this. Okay, check this table. This table contains 4 columns and 3 rows. Equation: x2 intercept when x equals 0, x1 intercept when x2 equals 0, and this is a point x1 and x2 on the line. Okay, now check the first equation. x1 plus 2x2 equal 2000. If x1 equals 0, then the remain is 2x2 equal 2000. x2 equal 2000 over 2, 1000. If x2 equal 0, then x1 equal 2000. So the points 0, 1000 and 2000, 0. So the common is 2000, 1000. Now let's Go to the next equation. x1 plus x2 equal 1500. Of course, x1 equal 0, x2 equal 1500, x2 equal 0, x1 equal 1500. Okay. x2 obviously equal 600 and x1 equal 0. x1 axis, x2 equal 0, x2 axis. So plot each equation on the graph. Now we are facing three equations where the first point, three equations corresponding three constraints. Now we are going to plot these three equations on the graph. Let's see how we can do this. Firstly, x2 equals 600 when x1 equal 0. This is the last. So the common points for the first constraint 2000, 1000, and the common point for the second constraint is the 1500 and 1500. D'accord? So now after plotting the various equation on graph, we found these the border point A, B, C, D. A is given as 1000. A represents x1. A equal 1000, 2000 when x1 when x2 equals 0. So 2000 0, and check D. D it is 0 600, the last constraint, the third constraint. Problem concern with 2 points C and B. Sorry, B and C. B and C are the point of intersection of lines or equation x1 plus 2x2 equal 2000 and x1 plus x2 equal 1500. So we need to solve this in this simultaneously. The intersection point between C and B, we need to solve this equation simultaneously in order to find the values of x1 and x2. Let's check the following table to show how we calculated. So now check the three corner points. A, x equal 1500, x2 equal 0. The intersection points B, x1 equal 1000, x2 equal 500. The next intersection point C, where x1 equal 800 and x2 equal 600. The last intersection point is x equal 0, x2 equal 600. Now we are going to substitute these values into z or graphical or objective function. Objective function state z equal 3x1 plus 5x2. When the corner point is A, where x1 equal 1500 and x2 equal 0, then z equals 3 times 1500 plus 5 times 0. So the result is 5500. Let's move to the next corner point B, where x1 equal 1000 and x2 equal 500. Okay, so z equal in this case 3 times 1000 plus 5 times 500, and we got 5500. Let's move to the next corner point where C, where x1 equal 800 and x2 equal 600. Let's substitute this value and we will get z equal 3 times 800 plus 5 times 600. The result is 5400. The last corner point where D, where x1 equal 0 and x2 equals 600. So it will be z equal 5 times 600 equal 3000. So once we are looking for profit maximization, then the best choice is to produce 1000 units of x1 and 500 units of x2, because this combination gives 5500 profit. Therefore, the maximum value of z occurs at B 1500. Hence, the optimal solution is to produce x1 equal 1000 units and x2 equal 500 units. Okay, write the dual of the following LPP. Given minimization zx equal 3x1 negative 2x2 plus 4x3. The constraints are 3x1 plus 5x2 plus 4x3 more or equal 7. So okay. Constraint 2, 6x1 plus x2 plus 3x3 more or equal 4 is okay. 7x1 negative 2x2 negative x3 less or equal 10. This is not okay, because this constraint less or equal, and the constraints of minimization must be more or equal. The first constraint is x1 negative 2x2 plus 5x3 more or equal 3, and the last constraint is 4x1 plus 7x2 negative 2x3 more or equal to x1, x2, x3 more or equal 0. Solution. So this primal of minimization has 3 decision variables: x1, x2 and x3. The coefficients of these variables 3, 2 and 4. The constraints are 1, 2, 3, 4, 5. This LPP has 5 constraints, respectively has 5 constants. Now, what is the expectation? Of course, minimization should be converted into maximization, given the coefficient of the dual must contain 7 7, 4, negative 10, 3 and 2. Once the primal problem has 5 constraints, respectively has 5 constant, then the number of variables of dual must be 5 variables. And the number of the constraints in the dual must be 3, because the variables in the primal are 3. Let's see. Since the objective function is of minimization type, all inequalities have to be changed to type more or equal. Constraint number 3 will be changed to negative 7x1 plus 2x2 plus x3 more or equal negative 10, and that is. Now, based on the mentioned procedures and steps, the dual LPP should be constructed as follows. Max Z equal 7y1. 7 is the constant, remember, return back. 7 is the constant of the first constraint of the primal. On the right hand side of the first constraint of the primal equals 7. The right hand side of the next constraint in the primal equal 4. So the next variable is the coefficient of the y2 must be 4 plus 4y2. The next coefficient of y3 must be negative 10. So after y negative 10, because the original is less or equal 10, After the transformation, we got negative 10. So negative 10y3 plus 3y4. 3 is a constant of the force constraint, plus 2y5. 2 is the last constant of the last constraint. Subject to, let's see, 3y1 plus 6y2 plus negative 2y3 negative 2y4 negative 2y5, and that is let's see, the first constraint is 3y1 plus 6y2 negative 7y3 plus y4 plus 4y5, that is less or equal 3. What is the 3? 3 is the coefficient of x1 in the primal linear programming, and so on. 5y1 plus y2 plus y plus 2y3 negative 2y4 plus 7y5 less or equal negative 2, and 4y1 plus 3y2 plus y3 plus 5y4 negative 2y5 less or equal 4. Check the number of the constraints in the dual R4, R3 equal the number of the decision variables in the dual. Application. Example 1. The assignment cost is assigning any one operator to any one machine is given in the following table. Machine operator. Now, the matrix consists of 4 machines against 4 operators. Each machine should be assigned to one operator. The condition is satisfied. 4 machines and 4 operators. The cells inside this matrix contains the cost of assignment. For example, if we assign A to 1, then it costs 10. If we assign B to 2, then it costs 9. If we assign C to 3, then it costs 3. If we assign D to 4, then it costs 7. The requirement is to find the optimal solution using Hungarian methods. Remark, the red numbers represent the matrix, the body of the matrix. Now, this problem gives 3 machines and 3 operators. Each operator assigned to one machine, and each machine should be assigned to one operator, as we mentioned before, on the basis of 1 to 1, on the basis of 1 to 1. Now we are going to apply the Hungarian methods using the previous steps or instructions. Subtraction or row subtraction, then column subtraction, then to draw the lines which will cover the rows of column which contains a minimum number of zeros. If the lines equal the number of columns or the number of rows, then we get an optimal solution. To reach the optimal solution means that the lines should equal, the number of lines should equal the number of rows or column. The expected number of lines is 4. The expected number of lines is 4. 4 equal number of columns, 4 equal number of rows, 4. Okay. The practices of row subtraction. خفض الصفوف وتنقيص الصفوف وطرح الصفوف. Now, referring to the given matrix, the cost inserted in the first row are 10, 5, 13 and 15. The least cost in this row is 5. Please refer to the given problem. Now we are going to subtract the smallest cost, which equals to 5, from each element of this row. Then 10 minus 5, 5 minus 5, 13 minus 5 and 15 minus 5. The result is 5, 0, 8, 10. Then move to the row number 2. Check your given problem. In the row number 2, the costs inserted in this row are 3, 9, 18, 3. Then the least cost is 3. Should be subtracted from the remaining elements of this row. 3 negative 3, 0. 9 negative 3, 6. 18 negative 3, 15. And 3 negative 3, 0. Move to the next row, row 3. The cost inserted in this row are 10, 7, 3, 2. The least cost is 2. This 2 should be subtracted from the remaining cost. 10 minus 2, 7 subtracted by 2, 3 negative 2, and 2 minus 2. The result is 8, 5, 1, 0. The last row is consisting of cost 5, 11, 9, 7. The least cost in this row is 5. Then 5 should be subtracted from the remaining cost. Then 0, 6, 4, 2. As you see, each row, the first row got 1 0, the second row got 2 zeros, the third row got 1 0, and the last row got 1 0. At least, when we mentioned before that, at least row should get 1 0, except column number 3 has no 0. Of course, the number, now we are not going to apply the lines. We are going to jump to implement the second operation, which is known as column subtraction, using this matrix. We will apply the operation of column subtraction using the matrix after the row subtraction, not referring to the origin problem, referring to the problem after the row subtraction. Okay, put into account. We will deal only with new matrix, after the operation of the row subtraction. Okay, we are going to choose the least cost from this given matrix. Now, referring to the previous problem, just look to the previous problem and focus on the columns. Focus on the columns. Now, the least costs, we are going to choose the least cost in each column. For example, referring to the previous matrix, the least cost is in the previous is 0. So if we subtract 0 from the remaining cost, the column is remain as it is. Also, this case is applied to the next column and to the last column, except the column 3. The least cost in the column 3 is 1. This one should be subtracted from the previous from the other cost. Then we will get 7, 14, 0 and 3. Now each column and row has minimum number of zeros. Now the next step we are going to cover using lines to cover the rows or the columns which consist of zeros. So we can of course easier column 1, column 2, column 3 or column 4 or row 2, row 3 and column 1 and column 2, whatever. Now the number of lines equals the number of columns equals the number of rows equal 4. Then the assignment is said to be optimal. Respectively, machine A should be assigned to operator 2, cost equal 5. Machine B to problem or to operator 4, cost equal 3. C to 3, cost equal 3. And D to 1, cost equal 5. The total cost is the summation of the costs 5 plus 3 plus 3 plus 5 equals 16. So when we assign machine A to operator 2 and B to 3 and C B to 4 and C to 3 and D to 1, we will get the minimum of the cost of assignment for machine to 4 operators. This is what is known as the Hungarian model in its, of course, simple way.